If you charge your phone to 100% every night, you're probably losing years of battery life over one thing almost nobody checks. Same lithium chemistry, but one battery outlives the other by 13 years. Here's the puzzle. You replace a phone or its battery every 2 to 3 years. But an EV pack is warranted for 8 to 10 years, and plenty last past 15. The obvious guess is that car makers use some exotic, better cell. They don't. The chemistry inside both is nearly identical. The 13-year gap isn't magic. It's engineering. Start with how batteries die. There are two clocks running. One is calendar aging, the slow fade that happens just from time passing. The other is cycle aging, the wear from actually using it. A cycle is one full charge and drain, 0 to full and back. Every lithium cell is rated for a finite number of these. A typical phone cell is good for roughly 500 to 1,000 full cycles. After that, it's still alive, just weaker. Both industries draw the same finish line, 80% of original capacity. When a battery can only hold 80% of what it once did, that's the practical end of life. Think about what that means in a phone. If you charge and drain it once a day, 1,000 cycles is under 3 years. That math alone almost explains the 2-year phone. But here's the twist. The exact same cell chemistry wired into a car sails past 1,000 cycles and keeps going. If the finish line is the same and the chemistry is the same, something about how the cell is used has to be different. 3 somethings, actually. And the first one is hiding in plain sight every time you plug in. The first difference is the charge window. Watch what your phone does. You plug it in and it races to 100%. You use it all day and let it slide towards 0. That full range, packed to the brim and run to empty, is the single most stressful place a lithium cell can live. The very top and the very bottom strain the cell every time you go there. Now look at the cars. When your EV dash says full, the pack is not actually 100% full. And when it says empty, it isn't truly empty. Car makers hide a buffer at both ends. The battery you paid for is bigger than the battery you're allowed to use. Full on the screen is really around 90% of the true cell. Empty is really around 10%. You never touch the punishing top or the punishing bottom. So while your phone lives at the extremes, the car spends its whole life in the calm middle of the tank, the gentlest range for lithium. Same cell, but one is constantly stretched to its limits, and the other is deliberately kept relaxed. That buffer alone dramatically slows how fast the cells wear out. But keeping the charge in the middle only fixes one attacker. There's a second one, and it's the real killer. Now the real killer heats. Lithium cells hate being hot. As a rule of thumb, degradation roughly doubles for every 8 to 10 degrees Celsius the cell heats up. Warm a battery and you don't just tire it, you cook it faster. So where does your phone live? Against a processor that runs hot, sealed in a thin metal body, often charging inside a warm pocket or under a pillow. A phone cell routinely sits at 35 to 45 degrees Celsius. It has no fan, no coolant, nowhere for the heat to go but into the cell itself. The car does the opposite. An EV pack is wrapped in cooling channels, thin pipes of liquid coolant threaded between the cells. That system can both cool the pack when it's hot and warm it when it's freezing. Its whole job is to hold every cell near an ideal 20 to 25 degrees Celsius, whether you're flooring it on the highway or fast charging at a station. Think about that gap. The phone bakes at 40 while the car cruises at 22, and heat is the thing that ages cells fastest. Same chemistry, but one is left in a hot pocket and the other gets an active cooling system. Which raises the last question. What actually decides how fast and how safely each one charges? The answer is the brains behind the charging. Fast charging feels great, but shoving energy in quickly generates heat and stress inside the cell. Every EV pack has a dedicated controller watching over it. It's a small computer that monitors and protects every cell in the pack, and it's called the battery management system. This system does the work you never see. It balances the cells so no single one gets overworked. It slows the charge speed the moment the pack gets too warm. And it manages that hidden buffer automatically, so you can't accidentally push the cells to the punishing extremes. The battery management system is basically a full-time bodyguard for the battery. Your phone has protection too, but it's playing a different game. Phone makers compete on thinness, on fast top-ups, and on price. A phone is built to be slim and to charge in half an hour, and longevity comes second. There's a physical problem too. The whole thing is one tiny cell with no spare room. There's nowhere to hide a big protective buffer and no coolant loop to squeeze in. So the same chemistry gets pushed hard, kept hot and charged fast, with almost none of the margins the car enjoys. 3 protections in the car. Barely any in your pockets. So the whole thing clicks together. Identical chemistry, opposite treatment. The EV wins those 13 extra years with 3 moves working at once. A hidden buffer keeps its cells in the calm middle instead of the stressful extremes. A liquid cooling system holds them at a gentle 22 degrees instead of a baking 40. And a smart controller balances the load and throttles the charge before anything gets hurt. Your phone throws all three away, on purpose, in exchange for being thin, fast to charge, and cheap. Push the identical cell to its limits, keep it hot, charge it hard, and it wears out roughly 7 times faster. That's the entire 2 years versus 15 story. Not better chemistry, better manners. And here's the useful part, you can borrow the car's playbook. Charge your phone to about 80% instead of 100% and keep it out of the heat. Do that and your phone cell starts behaving a little more like an EV's, buying you extra months, maybe years. So battery lifespan was never luck of the chemistry. It's a stack of engineering choices, and now you can spot every one of them. Next question, what happens when even the EV's pack finally retires? And could solid-state batteries rewrite these rules entirely? That's where we're headed next.